mutual communication they are not able to do. So let us try to take them also along with us. If at all there is a doubt, let us, like, if you need me to write down, let us do it at the end of it. Okay? And if you have tried out and you are able to do the homework questions or the practice questions, it is fine. If you want to do anything further, all of you are welcome to come and meet me personally in my sitting place, that is in Modla's third floor, room number 267, Hillside. A few of the chemistry people have already visited, so you can take help of them how to reach over there. Shall we go ahead with the further topic? These are the things we discussed. We just got introduced to statistics, the different quantities, different parameters like measuring tools, the persons involved, environment which are affecting the measurements. Then we had discussed the results of measurement, the appropriate way of representation. For that, we have learned different terminologies like accuracy, precision, standard deviation, place value, significant figures, rounding of rules, error propagation rules. Then we have applied all these together to arrive at the final calculation result and the proper way of representation of the result with the value, the standard deviation, other name is uncertainty, and the unit of the quantity. Now we will try to understand further what do we mean by error. When do we get error? Whenever we try to measure any continuous variable, there is a chance that by repeating the measurement, you are not landing up in the same value as you obtained before. And whenever we have large set of data, in research also you will see that if you are studying some particular property, you have to do large number of data, or you may have to collect large number of samples. What we will do, we will take out some random points from the entire set of samples. For example, if somebody wants to know whether you are able to follow my class or not, so they will come and randomly ask one or two of you, have you understood? Then whatever reply you give to that question, they will take as the answer of all the students sitting in there. So randomly we pick from many of the points of the entire sample. The entire sample, the terminology in statistics is population. Okay? Larger perspective. From that we pick up some points that we call a sample. The students who are asked to answer the question, whether you have understood or not, those are the samples. And the entire class is the population. Okay? And the students may be from physics, one or two of you will be called, from chemistry, from biology, from engineering, like that. Representative students, whoever speaks up fast, they will give the answer. So from, like that, representative samples are taken out from a large number of data, and we assess, we analyze this representative sample, calculate the mean value, then the standard deviation, then we extrapolate this behavior to the entire population. Okay, the set of samples which we collect and do the analysis, that we call as representative or the sample, and the mean value we calculate standard deviation. Then the equations are given here. Then we extrapolate this information to that of the entire class, rather than asking the entire students what is your opinion about this class. And in statistics, till date, the prevalence is that when you are giving the data of representative samples, we use English alphabets to represent. For example, if you want to show the mean or average, we write X bar, X bar, like that. And standard deviation, yes. The same thing, if you want to represent for the entire population, we use Greek alphabets, like mu for the average, sigma for the standard deviation, sigma square for the variance. Okay, Greek, wherever you see Greek alphabet, that means the extrapolated data. English alphabets means the real sample analysis data. That is why in the calculation of variance, you see there is a difference in the denominator. N minus 1 for the sample, N. Here also you can see, if not a difference in English and Greek alphabet, preferably lowercase letters for the small population, small sample, uppercase letter for the larger sample. If not, there is a difference in the Greek or English alphabets. So you can see in the population, we use the uppercase N as the total number of individual points in the entire population. That we had discussed in the very first class, second class, regarding the definition of standard deviation for small number of data and larger number of data, why there is a difference in the denominator. So if we measure a quantity 2 or 3 times, definitely if it is a continuous variable, you will land up in different values. That is a natural phenomenon. Any natural continuous variable, if you try to measure, it is very rare that the second and first measurement are landing up in the same absolute value. There may be fluctuation or variation. This we call as random variation, random distribution. We had seen in one of the examples, many groups of people were measuring the length of a road. Do you remember? 5 different groups were asked to measure the length of a road. Then we had seen which group is more accurate, which group is less accurate, which group is more precise, like that we had seen. So there, if you go and recollect or if you can check, you will see that none of the two values are identical to each other. If you are getting identical values, maybe it is a manipulated data or it is from different sets, different origins of population. Otherwise, your measuring device is not able to visually separate them out. That may be one reason. The least count of your measuring tool is not that to the mark to get the differentiation visible. So if you try to understand what is error, error is nothing but when you are trying to extrapolate the sample to the population, instead of reaching to the right point, you may be landing either on the higher side or on the lower side. So this will definitely lead you to some variation, some difference between the actual value and the measured value. This we call as error. This error has got two components. One is the bias and another one is the standard deviation. That we had seen and we had discussed with the circle and the dots measured value. There we had kept one thing pending to compare between which one will be better. Between two figures on the topmost in those set of figures. Do you all remember that we had kept us pending? We will discuss it after 5-6 classes. That today it should be clear. If not clear, today there will be an exercise at the end of the class that by that time we will understand which one will be better. So that way we can measure the experimental error accordingly. If you find out there is a finite variation, visible variation from the actual value, you can try to pinpoint which step you have done a mistake. You can go back and check each and every step. Accordingly, we will try to modify. Doing that, we have seen that whichever step has got the largest standard deviation, our focus will be to improve in that step. So that way we can efficiently come out with the better result, better quality result. For that only we have done the entire exercise of significant figures, rounding of rules, and understanding which part is giving larger contribution. We have seen length measurement, radius measurement, which one will be having higher precision, higher this thing, lower standard deviation. Higher precision, definitely lower standard deviation. So this way, knowing the properties of the measured values, one can modulate the results and come out with quality data which will be presentable and meaningful also. This terminology all of us know. Absolute difference will be in like this parlance. What we do is take the difference between the measured value and the true value as the absolute error. In some textbooks earlier, they used to give us true value minus absolute value. Right now, the prevailing rule is that go for the difference from your value, measured value, to the absolute value. Measured value minus absolute value. So if you have a positive error, that means measured value is larger or higher than the true value. If the measured value is smaller, definitely the error will be, absolute error will be negative. Whenever we say relative, that means the base value is taken in the denominator. When we said the relative standard deviation, we had taken standard deviation upon the average value. Here also when we say relative error, the difference between measured value and actual value divided by the actual value. It should be the actual value or true value. When you convert it into percentage, it becomes relative error in percentage. In standard deviation, we had used the term coefficient of variation CV. The two terms are now familiar to all of you. Now, absolute and the relative error. Today it is just like theory. Are you feeling bored? Like in between, we will have some interaction also. Some question answer or some numericals. You like numericals or theory more? But for that, we have to like introduce some new terms. Huh? So let us try to go forward faster so that we can come to that interactive session. So different types of errors are gross, systematic, and random errors. Whatever we do in statistical analysis is try to address the random errors and minimize the contribution from random errors. But for completion, we will learn what is gross error, what is systematic error. Gross error is nothing but you can just simply visualize it as something wrong or some error, some mistake from the maybe from the experimentalist or due to the instrument or the measuring tool, maybe due to the property of the material. While doing the measurement, the property is getting changed. Maybe, for example, if you are measuring the volume of a liquid, the room temperature itself is changing. Definitely, there will be fluctuation, variation in the room, like a volume of the liquid being measured. Maybe if your instrument is not properly aligned for that measurement, that time also you will see a large variation in the measurement. Sometimes it may so happen that measurements are right, but while noting down, you have done a mistake. That is also a type of error only. 25.8, but you have written 28 point. That is quite obvious. It may happen like that. You may write down as 28.5. It is very difficult at that point of time to pinpoint if this was an error. Finally, when you land up in a known quantity if you are measuring, then you will see that instead of reaching to the actual value, you are far. You are on the higher side. Then you will go back and check it. Then you will find that yes, this was a small error, small mistake while taking down the readings. That is why all of us are advised to take reading as and when it is measured, rather than memorizing the things and going back and making the notes. That is why when you do work, you have a laboratory record book along with you. All the time, whatever measurement is done, maybe you found that you have committed a mistake while doing the measurement. Even then, you note down the reading, and on the side you make a note. This was discarded due to some mistake during the measure. So this will help you out in further not committing the same mistake again and again. That way, proper record keeping should be done whenever you do research, or even for that matter, whenever you do some job. Keep a note of procedure, whatever you are doing. Keep a note so that it will help you either or the follower, whoever is following your procedure, they will also note down. While taking the weight measurement, I have to keep be aware of these all problems. I should take much care on those parts. So that way your notings will be helpful. Okay. How will you identify there is a gross error? If you plot the measured data, then and there itself, if you will see that the one of the data, if it is falling visibly, noticeably far from the rest of the data, you will be able to pinpoint as this red or orange color dot or circle is far from the rest of the points. The others form a group. Then you can say that this orange circle is the result of some faulty measurement. If at all, if you plot them and they follow some particular pattern, your one particular point is not falling on that pattern, then you can call it as some outlier, which is lying farther out from the rest of the measurement. Visibly, you can pinpoint. How can you do mathematically? Like sometimes it will depend on your perception. Maybe you will draw the curve a bigger, larger bell-shaped curve, then it becomes inclusive. If you make a narrow curve, larger number of data will be called as outlier. So how can you do the real calculation and find out, pinpoint which one is an outlier, which one should be taken inside? For that, this type of test, once you understand this one, this definition, we will do one numerical. The ISO recommended test for treating the outlier. One such test is Grubbs test. This is the name of the scientist who has proposed this test. The symbol for doing the Grubbs analysis, that is uppercase G, which is defined as the ratio of the difference between the suspected value, the orange colored circle in the previous figure, to the mean value. Mean is average or the mean of the entire data. The difference on the numerator, absolute value, divided by the standard deviation. X minus X bar by standard deviation. If you are not taking the absolute quantity, modulus of the quantity, you will have a symmetrical double-sided distribution as shown in the previous curve. Generally, we have the two-sided Grubbs distribution curve, and this is what I was telling you in the last class. Whenever you have, for example, when we were doing the logarithmic calculation, you asked me where from I will get the logarithmic data. That day I told you, if at all you have to do the rounding of the input data will be given to you. Like that, if you have to calculate the Grubbs value, this type of table will be given to you as a reference point. What you do is, you have a set of data, you will calculate the Grubbs value, G value, and refer to this table. The number of points, the number of measured points is the sample size. And the right hand side column is the critical value, G critical. Normally we write G subscript critical. And we compare the calculated G value with the critical values of G in the table corresponding to the number of measurements we have done. For example, if we have done 4 measurements, we will have a G critical value of 1.481. Okay, number of measurements corresponding to that, what is the critical value of G? It is tabulated, it is well established values. These tables are available like logarithmic table we have in hand. Similarly, this is one type of statistical table for doing the outlier analysis. When they calculate, you calculate the G value using the equation. You have the G calculated, you have the G critical. If the G calculated is exceeding larger than the G critical, then you say that the point which we kept as suspect or outlier is truly an outlier. It is considered as reject, not part of this set of data. If at all G calculated comes out to be less than the G critical, then we say that it is not an outlier, it is part of this same set of data. So we include it as part of it. We retain it. Understood? If G calculated goes larger or larger than the G critical, the whatever data point we suspected. Here we do one by one data analysis, not a set of data together. One data at a time. If you have one data, doubtful data, do the G analysis, compare with the G critical and take a decision. Once you take or keep it aside, go for the other data. It will be always like that. You cannot do multitasking. You cannot do together for 2 or 3 data in a singular calculation. Have you understood the concept of G outlier? We have to calculate the G value whichever value you consider as a suspect to be outlier, using the equation, the value minus mean divided by the standard deviation, you get the G value for whatever be the number of data points. Then we have the G critical table for us. Then you take the comparison. Now that many of you may not have the calculator, standard deviation is already calculated and even the G value is also given. You people can note down the values. I will send you the slides once the lectures are over. Then cross check. Now I would like to hear your opinion regarding whether this value is outlier or not. 4 values are obtained for the nitrite concentration in a sample of river water: 0.403, 0.410, 0.401 and 0.380. So just by looking at the data, you feel that the point, the last value 0.380 seems to be noticeably lower than the rest of the set of the data. Should it be rejected or not? If it would have been rejected, let us see. If it would have been like just visual examination, we would have rightly rejected it because most of the other ones are above 0.4. But should we take a decision just by seeing visually examining or by applying some basic theory behind? Whenever you take a decision in scientific balance, you should have some solid support, solid evidence to do that. Reject or accept. You have to prove it. Prove your statement, each of your statements, your conclusion. Should we reject it or accept it? Reject. Everybody says reject, but some of you feel it is rejected. Huh? You felt rejected. Reject. No? How many of you are feeling it should be rejected? Raise your hands. How many of you feel that it should be rejected? Which one? We are looking at both the table as well as the value. We should look both at the table as well as the value. First, you have to calculate the value. Okay. First, you have to calculate the value of G. Then you should know how many data points you have. Now we have 4 data points. So the G critical would be read from the table corresponding to 4. That will be 1.481, isn't it? And the calculated value is 1.432. Which one is larger? 481. What is? You have to see the table afterwards. First you calculate. Then take the number of data points as the feed. Then you go to the table. This is only a small part of the entire table. I have not given you the entire table. It will be a big table containing large number of data points. Whatever is the relevant portion, that one only I have highlighted here. If you go to internet or any authentic website or any standard statistics textbook, this table is available. One thing you have to remember that while suspecting a data, when you do the standard deviation calculation, we do inclusive calculation. That data is taken as a part of the data set. Only after taking the decision, now this is rejected, then finally when you are presenting the data, you will redo the standard deviation calculation, modify the result. Unless it is taken, the decision is taken, we consider it as part of your population. Okay. When you are calculating the standard deviation for the denominator in the equation, you have to consider the suspect as a part of the data only. That is the most important thing you have to keep in mind. Okay. Otherwise, what will happen? Most of the time, it will be outcome will be like acceptance. Another Here you have to do the calculation of standard deviation, then go for the comparison. This one is another way of doing the same outlier test using Dixon's procedure. We call the term as Q test. Okay, this will be much easier to do. You have to just take the ratio of the difference between the suspect and the nearest to the range, or the largest to the smallest value difference. You need not have to even calculate the standard deviation. If at all you have large number of larger, say 10 or 12 data, it will be difficult for you to manually calculate the standard deviation. Whereas this one you can do even manually, just by visually examining the suspect value and the nearest value you can find out. You can write either in the ascending or descending order in their data. The suspect and nearest, you take the difference and take the ratio between this difference to that of the largest to the smallest value. So this will be much simpler to do. And the same way, if the calculated Q value comes out to be larger than the critical Q value, the same conclusion will be taken. If the calculated Q value is larger than the critical Q value, reject the suspect. If the calculated value is smaller, retain it. Okay. And comparison will be similar way. Go for the same number of same number of sample size. Sample size here means number of sample data points. It is not regarding the width or height or weight of the sample. It is the number. In statistics, the terminology is sample size means number of sample points, number of input data. We use the term sample quantity for saying the weight of the sample. Here you can see, as the number of sample points increases, the Q value, critical Q value, keeps on decreasing. Whereas if you go to the G value, when you increase the number of sample points, the G value, critical G value, increases. Just for you to note down. Keep in mind that when you have calculated G value, compare with the G critical, not with the Q critical, because G values are always larger than 1, Q values are always smaller fractions. So G table and G calculation and Q calculation both will lead you to decide whether some particular data point is an outlier or to be retained. Okay. Most of the time they make you to come to the same conclusion. And if at all you have larger number of data points, slight modification will be there, so that we have seen that when the number of data points increases beyond 30, the standard deviation becomes more truer representation of the population standard deviation. The denominator n minus 1 slowly goes and becomes n. So like that, there will be small variation in the calculation, but whatever we do here will be the simplest one, taking the difference between the suspect and the nearest and taking the ratio of that to the range of largest minus smallest value. Other term is range of the entire data. Have you understood this? Here the conclusion is already written. Since the Q calculated is less than Q critical, the suspect measurement is to be retained. So if I ask you to do similar ones, you will be able to definitely do. If you are able to do, then we will go ahead. Once we understand these concepts, then we will have a set of questions, not numericals, just quiz type of things will be there. Systematic measurement error, this term we had used in the definition of bias, error, accuracy, precision, when we were discussing all those things. For example, if you are doing a measurement doing the weight measurement using a balance where already there is a null reading, always you get a larger reading than the actual value. That is one type of systematic error. Or one person is always reading the meniscus to the lower one, irrespective of whether it is colored liquid or transparent liquid. Sometimes it will that person will always have some inherent error rather than following the rules. So these are the two different types of systematic errors. Now we will understand the thing by the definition. Systematic errors, they have got particular magnitude. For example, if a person always looks in the sideways only for a material, always he will have some angular dependence of visual examination. Always he will read from one particular side. But some people write with like the fingers pointed like towards the right side. Some people have a habit in writing fingers pointed towards left side. Some people write straight. No? So there will always be a right slanting for those who write to like keep the pen towards the right. The other way also. This way, if you observe the data, if you observe the measurement data closely, some just 5-6 measurements, you can come to the conclusion that yes, this person or this instrument or this procedure always gives me a higher value. So if you closely examine the data, that way you can verify. Once you understand that always he or she, any doubt? He or she makes the readings higher only. Accordingly, we can assess the data. So that much margin one can keep. So that way we can correct. If we are able to predict the behavior, we will be able to sort the problem out. First, we have to understand how the data is behaving. So that way, systematic errors can be addressed. Systematic errors can be completely cured. We can get rid of the systematic errors completely. Did you understand that? If we are able to judge the data and come to the conclusion that there is a constant magnitude and constant direction, always you get a larger value or always you are getting a smaller value. So you can give account for this variation if it is constant. But if it is unpredictable or you are not able to tell whether it will be larger or smaller, whether it will be positive or negative, it is unpredictable. That is random error. If you happen to have a systematic error, yes, you can correct it. So having systematic errors, one have option to get rid of it, whereas random errors one cannot. This gives the answer to the question we had kept aside. Okay. Among the two set of data, if the dot points were largely fluctuating, if at all they were spread in a larger part, it would have been difficult for us to tell the behavior. Whereas, even though the data points are clustered and far away from the rest of the data, you can predict the behavior. You can do account for the correction. Accordingly, you can get rid of the error and make it come to the true value more close. Okay, that way the answer is that the one having smaller spread, though it is away from the true value, from among the two on the top in that one. Slide number, I don't remember. Could anyone of you visualize those data points which we had kept for discussion? A dot, I have to, second lecture, I think, second and third lecture. There we discussed accuracy and precision. The data points which are clustered together or close together, having lower spread, larger precision, that would stand as the better one compared to the one having larger spread. Okay. If you have understood this concept, towards the end of this discussion also, there is one exercise for you to do. Systematic errors can be corrected appropriately once you understand the cause of the problem. Accordingly, you can address the problem. If you are not able to address the problem, at least mathematical correction can be applied, if not by experimental way. First will be by experimentally correcting the data. You will have several alternate ways to do the correction. If at all any of the ways of the correction are not helping, final way will be to apply the mathematical correction. Even with that one can get rid of the systematic error. Should I read through these things? Systematic errors will have same magnitude and same. That means always on either side of on one particular side of the true value. This can be measured and corrected. So you will see that the entire data point is lying to one particular side of the true value. That way you can correct. Vernier caliper, if initially itself it is not properly zeroed, all the readings will be given as larger than the actual value. So if you observe the data closely, you can see that all the values are larger than. Here what you can do, either you can check with another vernier caliper, or you can ask your friend to do the experiment, or you can change the sample. These are the different ways to check. One of these different ways will help you to sort out the problem. There are ways to sort out, but the thing is that systematic errors will not be revealed by repeated measurements. If you find that there is always a positive side deviation, if you yourself keep doing, always that deviation will persist. You have to try to pinpoint which point I am lacking in the measurement. Just by repeatedly doing, you will not come to know whether I am committing a mistake or not. Either you have to change the sample or the instrument or yourself with another person. That way you can have a check whether there is a systematic. Did you understand? All of you understood? So these are different ways of systematic errors entering into your measurement. For example, if a balance is not properly zeroed, as we have seen in the vernier caliper case, even without any sample, the balance reading shows 2 milligram, 2.00 milligram. If you keep something on the balance, you will see some weight, it will be 2.00 milligram more than the actual value, isn't it? See, if you keep different objects, and if one of the objects weight is already measured known to us with some other equipment, we can say, we can find out, yes, the balance is showing some wrong, erratic data. Here itself we can apply the correction. Sometimes you may not be able to do how do you calibrate the balance? How do you calibrate the balance? Standard weights. Standard weights. That is just to make it zero, whatever. In the case of tearing, this will not help you. 2 milligram. Sometimes it may be due to some inherent problem in the balance itself. You have to check it, whether the balance is showing the actual weight or not. It is always better occasionally you do calibration of your measuring equipment, whatever be. There may be standard operating procedure for your measuring device. Once in a while, whenever you find free time, try to calibrate the equipment and get yourself convinced that yes, the equipment is giving me reading properly. So that you need not have to do a large set of measurements, repeat measurements that you can avoid. Each and every equipment you have to occasionally calibrate and confirm the proper performance. Another problem will be the environment of measurement. If the environment is not properly maintained, if at all you are doing the radiation measurements and your mobile phone is kept aside, definitely some signals which are coming or transmitting through the mobile phone, that will affect the background of your measurement. That will add up to the radiation background in the reading. Always you land up in larger value. One thing is that do not use the mobile at that time when you do the measurement. Anyway, inside BRC, you are not going to use the mobile. Maybe similar sort of equipment. If you are measuring some radio frequency or some microwave equipment is there by the side, either you take your instrument away from the side or the other equipment you remove from that side. Okay. or you wait till that other person's experiments are over, then you start your experiment. If not, you give some protective gear to your equipment so that there is no effect from the other instrument. These are the different ways one has to take care of the environmental conditions so that your data is not going to be like unused after the entire set of experiments. I hope all of you could understand. Today you people are not speaking. Are you getting bored? Yes? So you want a break or what? So if you want a break, we will take break for 5 minutes and come back. Or anybody wants to discuss till now whatever we have, then you can come to, like, you can raise your hands. अगर किसी को डाउट है तो पूछ सकते हैं 5 minutes ब्रेक में. There are some points, yes. Critical values, yes. Pardon? Those you want to speak? No. How the critical values are determined, that is one doubt. How the critical values are determined, those are derived from large number of data points. Most of the statistical tables, whether it is a G table, Q table, Z table, T table, F table, most of these are from previous experimental data of a large number of data points, large population measurements. So these are tabulated from well established procedures. That way it comes out. Yes. किसी का डाउट है? Yes. इसमें this first you have to do multiplication वाला. Uncertainty is given ना कोई in the first. Okay. Uncertainty, you know what is uncertainty? Which one? Uncertainty. Derivative was the origin of that formula. But उसके नीचे एक formula दिया था for multiplication and division. SU square is equal to SU by U the whole square is equal to SX. Which one? L square you have to do first. You have to do stepwise. For L square, you have to apply the uncertainty propagation for multiplication. L square is nothing but L into L. There you have to apply 1. The second step will be L square by 8H. 8 is a constant, leave it aside. L square by H. It will be, you have to do 3 steps. One for this L square wala. Another one is for the division. Another one is for the addition. So it will be a 3 step. Constant in the case of multiplication and division, then we take relative uncertainties, they get cancelled out. Value by the uncertainty by the value. Relative means what? Uncertainty by the mean. So this constant gets cancelled out. Whereas, which one? Constant has got infinite number of insignificant figures. So the thing, uncertainty will be this infinity by 8. And when you do the propagation, this uncertainty by the value will get cancelled out. Okay. Actually, you have the slide with you. L into L. So there you apply UL by L. 5 by 125.5. The rules are given here. 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 This one. Here. This one. When you are multiplying with a constant A, You see the relative error calculation, sigma A by A gets cancelled out. Other things remain. This is the rule we take. This one. If you have understood this slide, these 2, 3 slides, even this trigonometric, whenever you require that time only. Otherwise, these 2 slides, this addition वाला एक slide पहले होगा. This one. Addition, multiplication, and the constant multiplication. This one will give you the entire thing, whatever we do in the calculation. This one we apply here. When you have weight h in the denominator, this rule is applied. Here it is written. If u is a weighted product of x and y, the same thing only we apply. Okay. This is the only thing we do. Anybody has any doubt? Otherwise, we will start in another 2-3 minutes. आप और एक बार करके देखिए. हाँ, ये रूल कभी भी आपको एरर प्रोपगेशन रूल में डाउट आता है तो दैट 2-3 स्लाइड्स विल डू. ये दिस आल्सो विल कम. You need not have to by heart the rules. Once you practice some 2-3 problems, it will come automatically to you. But there is no big deal of calculation, only multiplication. You are allowed to take a calculator inside the exam. Calculation.
We have to multiply this, then we have to multiply this, then we have to subtract, then have
You
to add
are
this.
going to get a degree of doctor. No? Isn't it? Isn't it? Later on, some stage in future, you will be standing there to teach your juniors. That time, like, you should be proud enough to tell that, yes, I can do it. Any doubt? किसी को डाउट पूछना है? पूछना है? आज कम है स्ट्रेंथ में. डाउट है? आज स्ट्रेंथ भी कम हो गया क्या? आज कुछ दूसरे ये है क्या? अच्छा, दोपहर को क्लास नहीं रखना है, बोलना पड़ेगा मुझे. Then all of you have done sign. वीकेंड में किसी ने ट्राई किया था क्या टू डू दैट न्यूमेरिकल? नहीं, यू डोंट डू. वीकेंड में आप लोग वैसे फ्री है ना? करते हैं क्या होमवर्क वगैरह? डिड यू डिड? यस.
पहले आपने क्वेश्चन किए
हाँ, वो सबके आंसर्स आर देयर इन द स्लाइड्स.
कैलकुलेट करूँ बहुत बिग है तो हम उसको एज इट इज ही लेके मतलब लास्ट में जाके राउंड ऑफ.
हाँ.
तो वो वैल्यू कितनी लेके चलनी है, मतलब कुछ अप्रोक्सीमेट 6 डिजिट तक ले लें.
एक्चुअली द अनसर्टनिटी में हमें आप मान लीजिए डेसिमल के बाद आपको 2 डिजिट रखना है. एटलीस्ट आप फाइनल एक्सप्रेशन में आप 3 डिजिट तक रखोगे, देन यू डू द राउंडिंग ऑफ. तो आपको 3 डिजिट तक रखना है. But this is not for all. Everybody should follow up to whatever digit is possible. If you have a large set of data, जितना आपको चाहिए उसका एक और डिजिट चाहिए आपको राउंडिंग ऑफ के लिए, और एक डिजिट आप रख ही लीजिए हमेशा. तो 2 डिजिट एक्स्ट्रा in all calculation, but there is no statement as such. This is by practice. Our seniors tell us ki at least 2 digits you keep, always retain. Do not round off. At least 2 digits Second, the first digit will be to help you to take a decision. That the one you are going to drop it. Because in the case of 5, you have sometimes ambiguity, whether it is to be stepped up or to be kept aside. So that time, at least 2 digits, if they are there, they will help you to take a decision. Okay.
में we got the answer in law.
हाँ.
तो हमने स्टैंडर्ड डेविएशन था तो हमने डेसिमल से ही निकाला था क्योंकि
डेसिमल से नहीं, सिग्निफिकेंट फिगर्स, नॉट डेसिमल, सिग्निफिकेंट फिगर्स.
उसमें जो आंसर था वो ऐसे था -2 -0.01. तो यहाँ पर ये 3 थी तो हमने ये
This one was that one where the standard deviation was not explicitly given. So udhar we have no other option than going for the last digit to be uncertain. If the standard deviation is given, then only the rule will apply. If there is nothing to see, where will I apply the rule? First the thing should be visible. Log में 3 तक क्यों दिया था? The question was log of something in which 3 significant figures were given in the initial itself. So whatever is visible to me, up to that only I will be confident to tell. If at all is not visible, I will not venture into tell कि वो सही था कि नहीं. Okay. Question में जितना था उतने तक ही वो रखा. That is the reason. Yes.
nearest means suspect के nearest value.
Suspect के nearest. Yes, yes. Shall we start again? Shall we start again? Everybody has come back? So there are 3 different general, different types of causes of systematic error. One is that due to inherent fluctuation in the inherent limitation of your measuring device instrument or some environmental parameter or while doing the observation. The environmental parameters also we have discussed. While observing the data, for example, if I am reading the meniscus of a liquid in the container, if I look from upside, always I see a larger value. If at all the liquid is being dropped from the container. If at all I look with the side as similar to that of the level of the meniscus, then I will read properly. If I look from down, always I will see a lower value. Sometimes even after repeated instruction, 1 or 2 of us may be doing the same mistake. What we will do? You will ask your friend to do that thing and find that always I am reading, misjudging, I am reading from the lower one. Maybe that is my inherent characteristic. Depending on my height, I am not able to hold the burette at my eyesight level. Always I read like that from down only. Always I get a smaller value. Then my friend will come and help me. Yes, you are always reading wrong. That way I can correct. Otherwise, you take a known volume of the liquid, certain number, and you will measure it. If you are reading 9.8, that means always you are looking from the downside when the liquid is dropped from the burette. That way you can correct. That means such type of errors can be like corrected properly. up in a holiday. If at all it is so, you may have to go and work on that holiday. Accordingly, you plan. So maybe on a Friday, if you are planning to do a lengthy experiment like that, then what you can do, either be ready to go on a Saturday, Sunday, or you plan some other experiment in that time slot and start this experiment on Monday. That way, one can judiciously plan the experiments once you understand that there is a chance of going wrong, like unidirectional measurements. That way, you can solve the issue. Sometimes some people knowingly misuse the instrument. That also will lead to systematic error. Even if the reading is 20.1, I'll write 22.1. I'll like on my own, I'll add. Some people like some even digits, no, to odd digits. So their own like they do the rounding of just while noting down itself. Even though we are advised to do the rounding of only at the end of the calculation. So these things will lead to positive systematic error if you are doing rounding up intermediate. Most of the time, rounding off leads to positive systematic error. And like instrumental parameters also. Some instruments are to be used in particular conditions. If you use a voltmeter in high resistance circuit, always you will see a loading effect. So accordingly, whether your equipment is ready in the conditions, whether the instrument is rugged to use in the condition, whether if you are measuring the pH of a solution, whether the pH meter, pH electrode is properly dipped in the solution, whether the pH electrode is filled with the saturated solution, calomel solution, whether the salt bridge is there. All these things you have to check prior to starting your experiment, actual experiment. For that, what you can do, you can repeat one of the experiments reported in the literature, and they have given the data of their results. Na? Whether you are getting the same results or not, that way you can cross check. Then start your experiment. It may take 1 or 2 days of your initial experiments only. You need not have to redo the precautions, preventions in the beginning itself. If at all there is an environmental problem, if your environment is not clean, first you can clean the table, working table, keep everything contamination free. Those all things you can take care of and start your experiment. Even then, it may so happen that something may spill, or some contaminant may get added up when you are adding some reagent, when you are putting on the instrument, maybe some higher power, some electrical fluctuation may be there in a particular day. For that, every day you can do, if at all possible, you can do a calibration of your equipment. Some equipments, they require calibration as a lengthy procedure. You cannot do the calibration every day. Then once in a week or so you can do. If at all your instrument is to be kept in a particular condition, temperature condition or pressure condition, maintain that condition. See to it that there is no gas leakage while doing the measurement. These are the precautions you can take and get rid of this systematic error. Okay. If at all required, you can protect the equipment. Maybe some instruments like if they are kept near the sonicator due to the sound or due to the vibration in the sonicator, if at all the balance is kept aside, you will see that the vibration is leading to change or fluctuation in the measured weight. You can either keep them at 2 different working tables, or you can keep the balance on a vibration free table, or you can use altogether a different laboratory to keep these two instruments separately. If at all not possible, finally you can account for the fluctuation. These are the different ways. And the mathematical correction is the last option to carry out. Now we come to the random, as I told you, systematic errors one can correct but not by repeated measurements, but by changing the experimental conditions, or like the experimentalist instrument or the measurement which you are doing. Once you assure that systematic errors are completely devoid of, you got rid of the systematic errors. Now there is random variation, which is unavoidable. Always it will be there. Itna bhi bole, afternoon mein you feel sleepy, na? It is unavoidable. So that time, like what you can do, keep in between, even if you chit chat, I don't mind, but regarding the class, not personal things. So that way you can like knowingly, with like your own knowledge, you can try to address the problem. To a certain extent, you will be able to reduce the effect of systematic error. Okay. You know that always I have a like habit of scribbling in my notebook. So among those things, my data will be like not visible to me. So what you can do, you can take a rough page to scribble down. Notebook can be kept clean. So that way the environmental condition can be kept like affordable for the clean measurements. If you have a habit of chit chatting in between experiments, you can take entire lunchtime and do the job, and in the afternoon you can start fresh for the experiment. That way you can plan the experiments effectively, efficiently, and come out with very good results. Anyway, there is natural fluctuation in any measurement. We have heard of uncertainty principle. If you start measuring a property in microscopic level, it will be very difficult to do the measurements, two measurements simultaneously. If you are going to measure the position of electron, then the momentum, there will be some uncertainty in the momentum. If you are going to measure the velocity, then the position, it is not very certain. Like that, if you are doing any measurement, you are applying some probe to the measurement. Definitely the measurement will be, the substance will be giving some signal. During the generation of the signal, the substance, its original property is getting modified. Whether it is visible to us or not is another question. So definitely, if you are measuring more than one thing simultaneously using a singular probe, there is more uncertainty in either of the data. So it is always better, one-to-one interaction will be better. One probe, one measurement. Two probes, two measurements. Always it will be better to go for one probe, one measurement. Your data will be much, much clean also. Too easy to interpret. But sometimes you may have to do multitasking. You have to do input one probe, you have to see laterally also, multiple outputs. That time, most of the days, you will be compromising on the quality of the data, though you are saving the time. It is up to us to decide now. Maybe at your fourth year, you have to complete a PhD. Maybe you will be doing multitasking. So you will be compromising on the data. It will be advisable to start working from the first year onwards systematically, rather than keeping everything aside and planning to do at the end of the day. Do systematically, and if at all required, you can do the repeated measurements also. completely, but we can minimize the effect of random errors. Whatever we have discussed regarding systematic, we have discussed three different types of errors: gross, systematic, and random error. Gross errors we have mathematically evaluated and corrected for. Grubbs test and Dixon's test we have done. Similar way we can do for our own experiments. Now systematic error and random error are there. Systematic errors can be corrected. Once you understand it is truly systematic, how you will be able to understand? It will have like particular magnitude, particular direction in a set of data. It cannot be like understood by repeated measurements, but you do the calibration, you will be able to know. And this bias which is generated due to systematic error can be completely corrected either by changing the experimentalist instrument or the procedure. Random errors are always there. What you can do is to minimize them by repeated measurements. Once you do the number of measurements, you will see the standard deviation value becomes under control. Even though it is not fully under control, you will be able to predict at least to some extent. So that way, the reduction of random error is nothing but the improvement in the predictability. Okay. These things we have already discussed how to get rid of the systematic error. You can predict if the instrument is calibrated in some other place and I am going to use it here, how it is going to behave, whether I can apply some correction factor, or you can plan the experiment carefully so that there won't be any variation. You can check the instrument calibration intermittently. Then reference quality control materials also you can analyze. These are the different ways of tackling systematic error. And the last sentence is written as participation in proficiency testing scheme. Did anybody understand what it is? Proficiency testing scheme. It is like attending exam. We have attended the class and finally whether we have understood the entire class or not. If you say that I have understood, how will the other person know whether you have done it properly or not? You will ask for the organizer to give you some exam. Then you answer the exam questions. You yourself feel confident. Yes, I could attempt 100% in the exam. You feel proficient to do the job. Once you have come to BRC, you have undergone a proficiency test through interview. Most of you might have undergone interview. So that was one proficiency test whether you are eligible to do the PhD or not. You have already qualified your MSc. Now the proficiency skill, it is like a skill test. You have demonstrated your skill, proficiency. By comparison with your friend who has not got into, you stand in better proficiency. That is why you are selected. In laboratory experiments, proficiency testing will be done via the results of your measurement. For example, one person is doing the measurement and reporting the data up to 4 significant figures. Another one is representing the result to 2 significant figures. Definitely the 4 significant figures, that one will be more proficient in doing the job. So he will be the choice. He or she will be the choice. So proficiency testing is the test of skill. Most of the time, it is precision testing, and accuracy evaluation also will be done. Proficiency testing, you can participate and get yourself evaluated and get confidence. Yes, if at all you are developing a new method, new procedure, new compound you are synthesizing, you can like participate in proficiency testing and demonstrate your expertise. So you get confidence. Further, you can guide the other person also. Systematic errors we can completely remove, but random errors we can only reduce. These are the terms you have to keep in mind. Random errors cannot be avoided. There will be some error, some residual random error always. Random errors are always there in your measurement. How can you reduce? You can do repeated measurements. You can do the experiment some 2-3 times. That way you gain confidence, and if at all you do mistake in the second time, you will remember, yes, yesterday while noting down the weight I have done this mistake. Today I will not do. You will be conscious to do the experiment. That way you improve the quality. And sometimes you can increase the number of like representative samples which you have picked from the entire population. Even you can increase the weight of the sample, increase the sample quantity. That also will be another way to do. And if at all you are able to understand the causative factors, you can try to control the variables. If the temperature variation is affecting my volume measurement, I can try to control the temperature of the measuring device in such a way that it is protected with some protecting gear or some insulating material kept aside, kept on the out periphery of the instrument. Like that, you can control the environmental factors also. Any doubt? Now all of you can be active. Try to attempt. These are like not big equations, only quiz, question, answer, point, answer. There are only 7 questions. The type of error encountered while noting down the time using a clock that is lagging behind by 1 hour throughout the measurement. Okay, I'll show you the entire answer together in a single click. It will come. Anybody else has got any other answer? No, no. Repeating a reading never removes the systematic error. True or false? True or false? Repeating a reading never removes the systematic error. किसी को false लगा था student नहीं? Anybody feels it is a false statement or true statement? It is true. Repeating a reading will never remove the systematic error. It will only reduce the random error, because already it is inherent. It is, if at all it would have been a gross error, it would have been visible to us. Systematic errors, sometimes they are hidden in a set of data, because all of the data done by particular experimentalist, all of them will have identical type of contribution from the systematic error. It is very difficult to find out by repeated measurement. What kind of error is parallax error, or viewing consistently from the wrong angle of all reading? Systematic error, observational error. Poor calibration of the instrument leads to which type of error? Systematic or random error? So that means all of you, even if you are not speaking, understood the thing. Good. The errors which are always of same size and sign under certain conditions are called. Now you understood that systematic error is there in the questions. All answers are systematic. Na? List 3 probable systematic errors while measuring an object on a balance. No, gross will not. Systematic error, environmental, observational, in this thing, instrumental. Those were the titles given in the slide. You can specify. That means your memory is also very good. You can specify. Those were given in the slides. But any one of you have any experience, you can share with us. Any environmental issue or observational issue or instrumental. Those are the just guidelines for us. These are the things. It will be possible. If anyone of you would like to share your experiencing systematic error while saying an object. Zero error. That was there. Once you have understood the broader category of the tree, it would be nice. I'll be more happy if you can pinpoint, like broader category is right. It is not wrong. I'll be more happy if you can give your own examples. करते वक्त पता नहीं चला. सैन सैन अगर temperature also you can see.
Raising the clothes to the color.
Yes.
There will be no deviation.
Yes. So different ways are there. You can like see whether the balance for wheels or for stands, whether they are properly kept. There is a bubble in the balance to show whether it is properly kept. That you can see if at all bubble is like slightly shifted, you can keep it properly. And while noting down also like you can check the calibration. If you keep the lid of the container, sometimes due to air which is trapped inside the vessel, that will also lead to systematic error. So it is always better that you remove the container lid while doing the measurement. If possible, your material is not reacting with the atmospheric conditions. So those things you can take care of. Okay. So you have to understand the material property before doing all these jobs. Whether the material is like hygroscopic, whether it absorbs moisture, if it is kept open. If you know the property, whenever you are taking a new chemical or material, try to understand whether it is safe to handle with bare hands, whether you have to wear mask. All those things you have to first read through. Material safety data sheet, MSDS, you have to read. Then only you start using it. Those are precautions, nothing to do with statistics. And the last one, the color change of the chemical indicator requires an overestimation of 0.04 ml. Calculate the percentage relative error if the total volume of the titrant. This one you can all do. Percentage relative error. Percentage relative error. How you will calculate? Here 10 for in the case of 10.0, that is the true value. And the error is given 0.04 for all the three cases. So percentage error will be 0.04 divided by that particular value for each of the A, B, C case into 100. So which one will have the largest percentage error? 10. But can we conclude from this comparison between 10, 25 and 50 ml? If the absolute error is same. If the absolute error value is same for all. So in that case, given a choice between 10 ml, 25 ml, 50 ml containers, 50.00 ml container, we will opt for 50.00 ml. But there may be some practical difficulty also. You don't have 50 ml of the solution at all. Then what you will do? You may have to compromise with that. If possible with 25 ml, we will go for that. If not, then with 10 ml only, you have to be more careful from your side so that the minimum error you will introduce from your side. Okay. There may be some inherent error. This 0.04 ml error is already there. It's like anticipated all the time. So the other thing is that you have to be more careful. In this set, nobody has any difference of opinion. Shall we go ahead? Now we have understood that repeated measurements always have some variation. They are not like all the time you hit the target, you reach to the same point. There may be variation, especially when we are measuring continuous variables. If you plot the number of hits versus the point where you are hitting, you will get the probability distribution. Like here, measuring the volume of a liquid using a measuring cylinder. measure the volume, transfer it to some other container, re-measure it. All the time you will not be getting the same volume. You will be getting different volume. So if you plot the probability of getting the same reading as a function of the reading on the x-axis, you will see that there is variation, distribution will be there. The center point, I will show you the curve. The center point in that curve represents the value which if all of us were asked to read the volume of the liquid in that measuring cylinder, most of us will have the value which is represented by the center point of that curve, peak point of the curve. Some of us may be very, very lazy to read down. Their values will be lying far from the center point. Like udhar ke udhar, you will sit and read the volume meniscus. Then your probability, you may be in the outlier also sometimes if you are very lazy. That means it will be beyond that blue shaded area. Blue shaded area represents a set of repeated measurements probability. Shall we see through this slide or you want to break now? Shall we see this one slide also or you? Yes? We'll try to restart tomorrow again from this one. Just we will try to complete this slide. Here, otherwise I'll ask you a question. All of you try to tell me what all you can comment on this curve. There are some things written on the curve. Is it visible to you? Center point, the peak point is marked with a vertical line as mu. Is it visible? And on the right hand side, when you are facing the slide on the right hand side, mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, like that, 3 different vertical lines are shown. Similarly on the left hand side also, isn't it? So if I say that this is a symmetrical curve, do you agree? With respect to mu. So this curve, it is written mu sigma. That means this curve is a representation of the population, not the sample. If it were a sample, it would have been written as x bar plus s, x bar plus 2s, x bar plus 3s, and like minus x bar minus those so and so in the left side also. All of you agree that it is a symmetrical curve. That is, I am not drawing on the board. If I draw, it may not be. It is better to read through this slide only. And what else you can make out? Vertical axis is the probability of a reading, probability distribution. Anybody wants to come and give a comment? Whatever you feel like. It is a blue shaded curve. That is one comment. Some portion is not shaded. That is also a comment. It has got a maximum probability on the center side. When you move away from the mean, the probability of getting that value is less. That means the volume of 43.2 ml or 43.2 ml, a person reading as 33.2 ml, probability is very, very less. Whereas a person reading it as 43.1 ml, probability is much high. That much you can make out from this curve. Na? Even this curve was not required. That was inquisitive key we could make out. Nobody will read 43 as 33. But 34, there is a chance that even though you read it as 43, you note down as 34. That is probable. Gross error. These are the things compiled here. If anybody wants to add any other comment, you can. Or you can draw this curve in your notebook and come with your own comments tomorrow. In addition to whatever is written here, zero deviation from mean occurs with maximum frequencies in the vertical axis scale. Symmetrical distribution of positive and negative deviations is there. And when you move away from the center to the periphery, center to the endpoints, you will see that it is almost exponentially decreasing. The function is given on the right side. So small deviations are much more common than larger deviations. And the fourth bullet point says that the total area under the curve. Area is obtained by taking the integral of that function. You will see that total area is 1. Total area is 1. And if you restrict the limits of that curve, shaded portion, from mu plus 1 sigma on right side, mu minus sigma on the left side, you will see that from the entire 1 unit area, 68.3% of the total blue shaded area will be covered by this. If you are not able to follow this one, next figure will show you. But since we are stopping in this slide, you try to make a graph. Either you can do the integration and see. Okay. Or you can even slightly measure the area also. If you plot it on a graph, then if you measure 2 sigma on either side and make the shaded portion area and compare with the entire area of the curve, you will see that 95.5% of the entire area is covered by this mu plus or minus 2 sigma. When you go to mu plus or minus 3 sigma, mu is the center point. Then you have 99.7%. So if you want to compare, like include the entire thing, mu plus or minus so and so, like larger the number along with sigma, number of sigma points, you will get inclusive one. But that at the cost of your accuracy. You are moving away from the mu value. Idea was to come closer to the mu value, but you want that all of my data should be a part of this population. Then you are giving a larger spread. Larger spread, then it becomes inclusive. If the BRC committee decided to take all of the people interviewed, then they would have kept the pass margin as mu minus sigma very, very large. But they have kept some mu minus some sigma. That is why above that one only have come to this level. Okay. So as you keep smaller the difference from the mu on either side, you are getting smaller area. If you are taking this particular curve, if you compare some other curve which is narrower than this one, then what will happen? Narrower the curve, larger will be the portion covered by a particular distance on either side. Broader the curve, smaller will be the area. Did you understand this one? अगर कर्व को हमने broader कर दिया था, then the area defined by particular distance from mu, particular distance, now I am not using the word sigma, particular distance, mu plus 1 step forward, mu minus 1 step. Then the area, if you have not understood, we will discuss tomorrow. Regarding this curve, any of you want to include, add any comment, tomorrow we will discuss from here onwards. Okay? You can note down whatever is written here. Your comments will be highly appreciated by rest of us, all of us. Okay? Try to do one thing. Maybe you can search in internet. You will get many things. You can search in internet or the textbooks given, or you can think on your own. Try to bring one comment, your own comment. I'll be happy to listen to you. Okay? Tomorrow while setting the slides, you people can speak out. This additional comment I would like to share with my friends or with all of us. I would be happy to hear to you. Here we stop today.
ये वाला मैम मैंने सॉल्व किया अभी approximately it is coming 4.9 and
Okay.
in the slide it is shown
4.7.
Which one?
That question would be. So first of all, I've taken L square, uncertainty in L square. So answer is coming here around 8833.73. Then I've calculated the value of L square upon 8h. That value is coming this only.
Okay, 382. This I remember, this number. But the rest of the
Then-
things I don't remember it.
Then uncertainty in L square.
Uncertainty you have
वो
taken.
ये आ गया इसकी ओरिजिनल वैल्यू हमारे पास 1.65 आ गया होल स्क्वायर
That is L square.
हाँ दिस इज फॉर L स्क्वायर प्लस 8h अब मैम 8h जब हम लेंगे तो 8 को हम यहाँ पे जब
Eight का जरूरत ही नहीं है. Actually,
एक्चुअल वैल्यू जब हम लेंगे तो उसमें 8 मल्टीप्लाई करेंगे या नहीं करेंगे
नहीं करेंगे, जरूरत नहीं है. आपको मैंने वो इक्वेशन दिखाया था वो स्लाइड में.
किसी से एक्चुअल वैल्यू जब हम
Actual value you have to get. This is error propagation.